Okay, right. We have been discussed about sampling. We will cover shortly on the pre-consultation. We will cover the measurement concept soon, right? Okay, right. There are a few things that you need to be careful, right? Let's say if if you are trying to come out a sensor to be able to detect cancer biomarker, right? So first of all, you need to do GCMS, right? So this is what we do. I think in 2018 we managed to publish together with the Prof. Krishna, right? We take the head space from different cancer type, right? And then we have to study which particular cases represent for certain cancer, right? So, for example, D canal only respond to this particular cancer cell, right? Whereby the other gases like benzaldehyde and so on, almost all cancer cell having this component, right? Like ethyl canal, I think CHM5303 only having this component, but quite difficult to replicate because we don't have this chemical, right? So we again, when we do the experiment, we need to pick up the component that we can replicate chemically in the lab, right? So those chemical either is quite difficult to get hold or it's very expensive, right? So in this experiment, we need to pick up properly. For example, dodecane also easy to get hold, but again, if you detect dodecane, it's difficult to differentiate between CHM53 or NCF7, right? Again, you can Google around what is A54, CHM53 or MCF. I think there are small cell, non-small cell of lung cancer. I think these are the cell for breast cancer, if I'm not mistaken, right? And then maybe you can correct me if I'm wrong later on. All right, okay. So these are the response, the typical response from QCM sensor, right? First of all, you need to sniff, right? This is the baseline, right? When you sniff, right, the sensor pick up the analytes and the response will goes down, right? And then when you push it back again, the sensor should be able to go to the recovery mode and then the baseline again. Now, let's say if you sniff on the baseline, right, and you push, somehow the sensor will not go to the baseline, right? Then you will have trouble to differentiate. Then you need to apply a signal processing and so on, right? So when you take a look of this result, right, you can tell that different analyte give different reaction to the sensor, right? The QCM were able to detect sharp rise of the methanol, but when you modify the what you call it, GO, graphene oxide, when you reduce the graphene oxide, you can see that the ethanol also behave differently. You no longer detect the methanol no longer sensitive. You will get a better sensitivity of the ethanol, right? When you put DGO, which I also forgot, I'm really sorry, I forgot already. What is DGO? Right? You can see that the behavior of the analyte are different. Right? So by having a different substrate on a different QCM, you can create a different pattern. Right? So when you have this pattern, you can submit to the machine learning, and it can predict for you which component or which chemical. This graph, right? You will get this kind of graph, right? Okay. Let's say when you have three sensor, right? When your sensor giving this kind of pattern, right? High, low, and high. Of course, ethanol, and isopropanol, they have the same trend, right? So it's going to be quite tricky. Try to differentiate between these three, right? So you might, from this result, you might need a different sensor as well to support the evidence. But again, if you have this pattern, low, high, and low, of course, you can clearly see that this is hexane, right? Because the trend are different from this trend, right? Because low, right? And then whereas if you take a look on it, they have the same pattern, right? Which are also difficult to detect these four. But again, you can apply another what I call it comparison. If the DGO is very high, right, compared to the GO, then most probably you will get ethanol. If the difference are not so high, then it's the best. You can say that this is ethanol, right? Having three sensor, it is quite tough to differentiate multiple analyte. You can differentiate only small number of analyte, right? Imagine if you increase number of sensor, right? You will have a different pattern, right? And it will help a lot in determine what kind of cases that you are dealing with, right? So that's why if scientists nowadays, I think they are trying to come up with the 64,000 sensors in one machine. I think they are managed to do that, right? I think they are moving to dot matrix as well, and to make it even bigger number. Again, when you have thousand, when you have a lot of number of sensor, you will have another problem of how to capture the signal, right? When you capture the signal, imagine you have 100,000 of signals, then you will have a problem how how to determine those cases, how to differentiate with one another, how to eliminate sensors that are not responsive, right? So those are the tricky part later on that we will go discuss now. Okay, right. So we covered to this part. So when you have response, then you need to subject it to the pattern recognition, right? You need to differentiate the pattern itself, right? Let's say if you have many sensor, but the sensor giving the same pattern, then we cannot use that sensor. We have to try to use different sensors so that each of different sensor giving a unique response, right? So this is another part that we have to consider as well, right? Not only we need to find the sensitive sensor, we need to make sure that the sensor behave differently, right? Okay, all right. So these are the another example, right? Let's say if it detect different concentration of different gases, you will see a different response, right? With this different response, you can clearly tell what sort of gases that it detect, right? But again, with the bare eye, with the naked eye, you have a difficulty to detect component B, C, and E, right? So you need to apply geometric or machine learning to help you in determine what sort of sensor, what sort of gases that you are dealing with, right? Okay. We will go to the next slide. This is the way it should flow. You have a sensor array. You need to extract the features. Once you extract the features, you have a lot of data, and then you need to reduce the dimension of data so that you will get some grouping. Right? From this grouping, you need to draw a line, and from there you can do the decision, right? Okay. Right. I think this is another approach that what scientists are doing, right? They are using exploratory data analysis, which is PLS or PCA, right? When you have a lot of sensor, right? You can't process each of them individually. You need to get the pattern, and then from the pattern you need to group them accordingly, right? So this is some sort of group that you get, right? Instead of looking at the single pattern, right? It's difficult to differentiate. Of course, you can see the difference between the pattern, but to be able to tell straight away is difficult. You need to observe clearly and then try to see whether they are different or not, right? But if you take a look on this uh, grouping, you can clearly say that there are 4 groups, right? This is how the mathematics useful to help you in differentiate the groups of pattern. Okay. Previously, some scientists also tried to apply, we call it a color pattern, right? But again, if you have a lot of sensor, right? If you have 100 sensor, if you have 1,000 sensor, this color pattern is quite difficult to differentiate. So, right, you see a lot of LED being dim or being different color of different intensity, right? It's hard to tell, right? Especially if you want to detect a lot of gases of a lot of analyte, right? Simply said, if you take a look of this 10 sample, right? It is hardly to differentiate between these two, right? Or these two. It's quite difficult, right? This is only to detect 10 sample. If you have 100 sample, right? I think the difference will be very, very little, and then you have a problem to use this concept, right? Okay, all right. Okay, and also if you receive this kind of signal also, right? You need to do something as well, right? This is the same signal from the same response, right? So you have a smaller response, then you sniff at the second time, response, and then you push, it goes back to the baseline momentarily, and then you sniff again, it goes high, you push, and it goes high, and then you push again, and it goes high again, right? What is really happening here, right? What do you think is happening here, right? This is happening purely because you don't really control the ambient temperature, right? You do it in the morning, and after a while, the ambient lab becomes slightly increased temperature by 1 degree, and the changes in the temperature will give you this effect, right? Because the difference are very, very small, right? If you zoom, then you will see the difference is quite high, right? Whereas this part also not so bad because the fluctuation are not very bad. But if you take a look on the shape, right, the shape of the response are different, right? This is due to the moisture in the air. You need to be careful because the moisture will affect the sensitivity or the behavior of the sensor itself, right? So when you are measuring any particular analyte, you have to make sure that the environment you are dealing with are quite consistent, right? And then when you measure, you need to measure uh, the gases in a short amount of time. You cannot measure for an hour, right? And then you compare again, and then try to replicate the sample. Of course, the result will not get similar. You'll get a different result. Then you will get headache to analyze this result, right? So you need to have a strategy. You need to plan out your experiments, right? Okay, so these are the real result that we have. This is, I think, this is the result that we get been published in this journal, right? We can see that there are baseline drift, right? Okay, this baseline drift is not so critical that you can correct again, as long as the steady state or the transfer response are almost the same, then it should be okay, right? So you can see that the first sniff you have a baseline at this range. Then on the next sniff you have at this range. On the other sniff and so on, it keep going downward, right? Until certain range, right? The baseline is going far below, and then your response also will become lower as well. This is you need to avoid, right? Okay. So this is either due to the temperature or due to the moisture. You need to be careful as well. It's difficult to determine, right, in these cases, because there are many other parameters that we cannot control, right? Right. So this is another challenge when we do measurement, right? Okay. These are the raw signal that we have from our system. You can see that a lot of noise. But again, the baseline is quite consistent. I think that's good. And also the response, although there are a lot of noisy signal, but you can see that they are quite consistent as well, right? That's why when we sniff the sample, we don't sniff one time or two times. Normally we sniff either 5 sample or we sniff 10 sample, so that we can determine whether the signal are consistent or not, right? If we sniff 5, you get this consistent, and then you can stop. You don't have to sniff longer. Okay. Any questions so far? Okay. If not, I'll move on. Right. So when you have this kind of noisy signal, you can smooth them. All right. If the smoothing is not enough, you can either even apply another technique, then you get better smoothing. All right. So from this, you get to this line, and then you can smooth them again. You will get very nice line, right? And from this line, you need to extract the features. You either get the maximum point from this sniff, or you get the steady state, right? Or you get the one before being purged, right? So normally you need to take a look on your data. You need to make sure that if you take the maximum peak of individual cycle, then this peak might not be consistent, right? But again, if you take the last sniff before you being pushed, you might get a quite consistent reading, right? Right. So this is another strategy when you apply feature extraction. First of all, you need to really understand the behavior of your result, the behavior of your data before you decide on the next page. Okay. Once you receive this signal, you extract the peak, you tabulate in the graph, then you apply PCA, Principal Component Analysis. Then the mathematical, the MATLAB will do nicely for you. It will group the what I call it, the gases within correlation. Let's say if we find this sample are correlated to each other, it will group them closely. If these three dots are quite close to each other, it will group closely, right? The problem that you will face is like you having this guy in orange, blue, and green are together, right? Of course, from the experiment, you know that they are from different type of gases, right? When we put in the grouping, you can see that they are grouped each other, right? Bear in mind, you need to know that the grouping was done manually, right? We ourselves need to group them, need to draw a circle around the dot, right? Right. Again, this process is not really convenient. Every time of the experiment, this one should be in one group, this one should be grouped together, this one should be separate from this group, right? It is quite tedious, right? It's difficult to determine whether this group belong to the same group or not, right? So you need to apply another technique, right? Or you need to apply LDE, linear discriminant analysis, for example, to make sure that you have a better separation, right? For example, this is again the PCA, right? When you see this group, if I don't share the label, I think most people say that this 1000 ppm with the 500 ppm should be together in this range, right? And again, it's difficult, right? So it's not as simply of plotting the result. You need to make sure that you are able to draw a single line from this result, right? Then when you do prediction, then you can when you receive a new sample, if the sample within this range, then exactly you declare this is H2. If the sample fall in this circle, it will become methane CH4 or otherwise. Okay, right. So again, we take a look on another sample, right? You get a lot of uh, clustering, right? Imagine if we don't put colors, right? Colors indicate different sample, different type of sample, right? If we don't put the color, most probably we will group them wrongly, right? We will draw this one big group. We will draw this one big group, and eventually we will have a three different group, right? Which is wrong, right? So again, PCA dimension reduction was not enough. We need to go on a high level, right? We need to go to the AI, artificial intelligence, right? Normally, you have this kind of pattern. For example, it's very difficult to draw a straight line to what do you call it, to isolate between the group, right? Right. So you need to apply a formula, right? So normally you need to transform the domain from non-linear to a very linear domain. Then you can draw a straight line. Whichever sample fall at this side, it will be treated as a sample A. If the sample falls on this side, on the right side, you can say that it should be in group B and so on, right? Okay, this will be the next step, right? If you're having if you're having this kind of result, right, then you need to apply non-linear method, right? Okay, let's say if you only test for a different type of sample, you only test orange, blue, and this light blue, right? You will not have a problem because you can see that they are clearly separated. As the number of sample increase, then your result is become complicated, right? So you need to use a complex algorithm as well, right? Once you manage to have this, you need to separate them in the straight line, right? Then only you can do prediction. Okay, my question to you guys: how do you predict the concentration in this range, in this grouping? Right? It's difficult. Right? Again, there is no single method. There's no single tools can do everything. Right? As I mentioned earlier, of course, you can use this method to do the grouping to differentiate between the analyte, between the smell, between the gases, right? But again, when you want to determine the concentration, you need to use a different plot, right? For example, you can use PLS, right? But partially square. Then you have to do calibration as well. So you have a reference concentration. You need to calibrate sample. These are the concentration, and then as you increase the concentration, you get the response increase, right? And then you subject it to the sample, and the sample will tabulate around this area. Then when you have the sample on the top, then you can really say that this is high concentration, and when you get sample at the bottom, and this is lower concentration, right? So normally it is safe if we do interpolate. Let's say if we have a result that outside of the range, then we need to extrapolate the result. But again, when you do the extrapolate, you need to verify again. When we have a result out of range, right? You need to make sure that the range is valid, right? Somehow it could be due to the other noise, skew, or so on. You need to be careful. Normally, I would suggest we should do the interpolate, not extrapolate the result. All right. Okay. Once you manage to receive to this area, I think you are almost there. Eh? Right. I think people were happy to see this result, and make sure you have the what you call it, the sensitivity of curve equal to 1. R R squared equal to 1. Once you receive this line R squared equal to 1, I think you are on the safe side, right? But again, if you deal with the biological sample, right, I think don't worry, R equal to 0.6, R equal to 0.7, I think is also acceptable. Right? You don't have to worry so much on R equal to 1. Okay, right. Okay, I think we are approaching to the end of my slide. Okay, now I'm showing to you some of the sneak peek of the next Inos. they targeted that Enos is going to be very small, handy, and then it will interact with your mobile phone, right? I think if nowadays if you Google around, there is a device that used for the dentist. They start using the Enos to detect the gum infection, the disease for the tooth, right? I think they are on the market already. Okay, these are the example of Enos, which is smaller and convenient as well, right? And then this is more for your homes, right? You detect the air quality, moisture, or VOC, right? And I think this is what scientists struggling to come up. And most probably, if this is successful, I think we could have early, early detection or early scanning for terminal disease like the cancer. Uh, it can become your personal healthcare. For example, every morning when you wake up, you could exhale into the system and it will tell you what sort of disease that you have. Right? I think these are what I call it, these are the idea that the scientists are moving forward. Right? So you have to go to the clinic. You don't have to go to the hospital to queue. Right? This will be your first line of defense. If system trigger or you are not healthy, then you trigger and then you should go to the hospital or clinics. Right? All right. Okay. I think that's this one. Okay. These are the system that they are using in Rotterdam. They are using Enos. Right. They deploy about 250 Enos. Right. I think Selangor should be using this as well. Right. They should be using Enos to detect what you call it, illegal dumping of chemical. Right. You know, everybody suffer when they shortage of water. Right. So the first line of defense, not only Selangor, I think we should start implement this. Not only Selangor, but also in Johor. Right. So we should put the sensor along the school, right? We should put along the river, around the industrial area, right? So by having this, we could detect any illegal dumping of chemical. I think Europe have done this. I think if you guys are able to go to one of these industry, you can propose to them. We should have used this Enos, right? Okay, I think with that I end my slide, right?
Okay.
And then I open for Q&A.
All
If you
right.
have a question.
So any question from you? I think this
Every
is
so quiet.
Yeah, I have a question. Can you
Yes,
please refer to the page 15?
page 15, yeah? All right. Okay, this one. Is it?
No. Yeah, yes.
Okay.
Actually, I have missed out the question. The point you are mentioning. Just now you said that if purge in the nitrogen or oxygen gas, and what is saturated, and what is the? I mean, what will it happen after the saturation?
Okay. All right. Let's say we bring this Enos to the site. Let's say they have a lot of reducing gases. Reducing gases such as NH3, something that gases that draw the electron from